this recording? Recording now, or yeah, okay, all right. I'm gonna let people move in. Actually, I'm gonna give it another few minutes. Yeah, so we'll send out a link for the recording after the end of the workshop. Holy shit, there's 60 of you guys. Okay. We will send a link to the recording after the workshop ends. Yeah, it will be posted on Discord. Our slides on the Discord. Yes, it'll also be uploaded on YouTube. Sorry. We're beginning to upload many of our workshops on YouTube, so we'll get there. What happened to the Discord message? Edward, you freaking added the wrong people. Oh my god. Edward, you added yourself, not everyone. Edward, please change your message. All right, 66 people, let's go. Let's give it like another minute and then probably start. Okay. I just pinged everyone. Yes, it is light mode. All y'all. What do you mean what this means? Oh shoot, we're gonna announce it in general chat. Okay, wait. This is a whole mess. All right, 74 people, let's go. If you have a membership account, remember the checking code today is neural network, replacing the L of 1 and E, the first E of a 3. We weren't expecting light themes. All right. Holy, that's like 77 people. Wait, Edward and Catherine, should we start now? Or do you want to wait a little bit longer? Okay, there's even more people. Okay, there's even more. Wait, I'm gonna wait a little
People
longer.
are still gonna dip in. We might as well start.
Yo, can you hit 100 people? Let's go. Okay, Edward and Catherine, start now or actually it's 4:35. We're actually already late. Okay, hi everyone. Yeah, today this is the very first workshop fall quarter. It's an introduction to AI and neural networks. It's being hosted by ACM AI at UCSD. Make sure to check out our website ai.acmucsd.com and join our Discord through that website. So today presenting will be me, Stone, and Edward. We're both from ACM AI. Checking code is neural network. Just replace the first 3, E of 3, and replace the L of a 1. you can make sure to join our membership portal on members.acmutc.org. All right, so what's first? What is AI? That's a pretty big question. Who just said, oh my God, okay. Yes, we love memes. It's a field, I think this is quoted from Wikipedia. It's a field devoted to exploring methods to exhibit intelligence in machines and produce intelligent agents. So this can be as simple as an if statement, like if weather is raining, bring an umbrella, else run outside, something like that. It can be as complex as a 100-page research paper. Like there are research papers that are huge and insane that you do not want to read, but that's how complex AI can get. Hi, Michael. And here's a nice meme. Programmer, if statement, is this AI? And that is true, that is AI. But AI also encompasses quite a lot of other things. To make things clear, AI, a lot of people get these terms mixed up all the time. AI is a big field, okay? It's a giant circle, it's that orange circle right here. Within AI, there's different subcategories, namely NLP, robotics, autonomous vehicles, computer vision, and many more. And specifically, can you use it for InstaBio? Yes, you can use it. Specifically, another term that's really worth mentioning is machine learning. Machine learning is a subcategory of AI, but it doesn't contain NLP, robotics, vehicles, vision. In particular, machine learning is a tool. It's a field that's basically a tool dedicated to developing this tool called machine learning to engage and better the many fields. Yeah, so let's move on. So this is just a couple of numbers. AI is pretty big in our world. It's been blowing up every year. Like it's been doubling, probably breaking Moore's law by a lot. Just a couple numbers, 37% of organizations use AI right now. About 4 billion devices already work on AI-powered voice assistants. So think about Siri, think about Alexa, think about Google Nest. Not sure what's it called. Yes, ML is a subset of AI. I think some people might argue differently, but it's basically a subset of AI. That's okay, Google. 97% of mobile users are already using AI-powered voice assistants. 63% of people prefer to message a chatbot just talking to a human when communicating with a business. These numbers speak to themselves, just showing how important AI is right now, and actually statistics, actually. It's very important. And in particular, just an example, in 2017, Netflix saved $1 billion by using machine learning, which is insane. Just a couple other statistics I can pull off the top of my head. In particular, Google applied machine learning to the energy industry, and they reduced energy consumption by a ton, like at minimum, at least 30%. So even though people are complaining that AI is using a lot of energy, it's also helping us reduce energy as well. So benefits outweigh the costs. Here's some just basic history. The concept of AI has been around for ages, but hasn't blown up until like 2012, which was when deep learning, which is a really popular buzzword term, became very popular thanks to a foundational paper by Geoff Hinton et al. And just better software and hardware. Before, it was only just science fiction, and pretty hard to understand or have working due to the fact that in the 1950s, computers couldn't even store memory. All they knew how to do was execute command. That's it. Think about those ticker tapes, those old giant IBM machines where all you did was just fed in what are called punch cards. All they did was just execute commands. They don't store things. Even then, given the limited computational abilities of computers and software, computer scientists like Alan Turing in the middle here already began asking big questions, and such as the Turing test, testing whether a computer could fool a human into thinking it was also a human. Supposedly, the first attempt was called the logic theorist, invented by Alan Newell, Cliff Shaw, and Herbert Simon, designed to mimic the problem-solving skills of a human. And I was like, not to worry, guys, this is just some basic AI intro first, just to cover broad AI terms before we move into the actual neural networks. And one of the more popular early successes came through ELIZA, developed by MIT Artificial Intelligence Laboratory. Basically, it was like a chatbot. It allows you to communicate and demonstrate the true power of NLP and help kickstart a lot of the enthusiasm for NLP. And then, yeah, it's a simple ability to just take your input and respond has really amazed a lot of people back then and helped kickstart that whole entire movement. And now moving forward, lots of fundamental work from people like David Romerhart, James L. McKillen, on things such as PDP, parallel distributed processing, and their work with Geoff Hinton in applying the also well-known backprop algorithm, which we will introduce to you guys in our next workshop, that allows neural networks to learn and optimize. Just a comment, nowadays, like modern day, the main competitors in AI are literally like these companies here: Google, Facebook, DeepMind, Amazon, OpenAI. TensorFlow is actually not a company, it's actually just a project, a framework for AI. And 3 of these are owned by Google. That's just to say how powerful Google is. And even then, Google has their own AI division and they own DeepMind, another AI company. So it's kind of insane. Oh, they also own Waymo. Waymo is a autonomous vehicle company. So like, I don't know what Google is doing, but they're very forefront in AI. So these are just some common terms you might have heard of that I do want to talk a bit, just to clear a lot of misconceptions. So here we have a couple things. Machine learning. As I talked about earlier, machine learning is more of a tool. It is a field dedicated to improving the tool known as machine learning. And machine learning is used to aid other fields, such as computer vision. Before the arrival of deep learning, convolutional neural networks in general, and improved hardware, computer vision was purely based on a lot of math, linear algebra, and thus. What's D&D? Okay. Back then, for example, computer vision used to rely on things called like image filters. You might have heard of things such as a Sobel filter, kernels, convolutional kernels, edge detection filters, canny edge detection. This is how it used to work. But nowadays, it's just all like convolutional neural networks. There's other things. There's automation. There's reinforcement learning, a really popular form of unsupervised learning, where you kind of just put an agent in an unknown field, in an unknown environment, and let it just learn itself. For example, reinforcement has been popularly been used to play Atari games, such as ping pong. You just let the player go into a ping pong game, no rules. All they know is they can move up and down, and they learn to win. Deep learning is a really big buzzword, which we'll go and talk about later. But another few things we also want to mention is also the hardware side. Your GPUs, TPUs, CPUs. What does this mean? What is a graphics card? Just a quick comment on those. CPU is what's on your computer. It's on your everyday desktop, laptop computer. It is what runs computations, does your ones and zeros binary operations. GPU is a very specific processor meant to, it's called a graphics processing unit. I think I got that right. It's specifically geared towards doing matrix operations, which we will visit later at this workshop. And the reason why it's so important is because using matrices really helps boost the computational capacity and speed of our algorithms. TPU is a specific thing developed by Google. I actually have no idea how it works, but it's better than GPUs and it's very fast. Yeah, there's a ton of words. We'll get through all of them in our workshop series. So AI is all about stats, simple or complex. It's not just about neural networks and deep learning. There's a ton of mathematical tools in the machine learning realm, and it does everything from data analysis, prediction, optimizations. These are some things you might have heard. Support vector machines, linear polynomial logistic regressions, linear quadratic cubic programming. You don't know what that is. It's basically given a linear or quadratic or cubic equation, find an optimal value given some linear constraint. Principal component analysis, does something called dimensionality reduction. We might get over to this in the future. Monte Carlo tree search, this was used by DeepMind to beat one of the best Go players. It effectively is just a brute force search of all possible decisions you can make and just chooses the best one. Gradient descent, genetic algorithms, literally an if statement is a bot, is an agent, and so much more. What else did I say? Yeah. But AI is also about systems. This is an entire other field about AI, which is ML systems, AI systems. Under the hood, a lot of computing goes into doing all these predictions and analysis in AI. And what we need is robust AI systems, robust cloud AI. So think about Google Cloud Platform. They have an entire AI suite of tools. Same goes for Microsoft Azure, Amazon. I don't know what their AI frameworks are called. Amazon has their own set. And a ton of other companies are doing this. I think bench learning is also kind of like, it's kind of a bench learning if you haven't heard of is like cloud bioinformatics, cloud biology, but they also incorporate AI into there as well. GPUs, TPUs, as you talked about already, hardware acceleration, parallel computing is really important. Quantum computing is another thing this is coming about. Someone actually in our Discord sent a paper about quantum computing to me, and its relation to AI, and it sounds really exciting. There's a ton of things: AutoML, auto differentiation, computational graphs, and so much, much more. Don't worry if these terms don't make sense. They don't make sense to me either. I kind of just pulled it from Wikipedia, and like I know half the definition. These are just some like basic applications. So automated driving, as you may have seen from companies like Waymo, Uber, and whatever. Image recognition, pretty popular, recognizing, let's say, a cat and a dog. Sentiment analysis, perhaps, let's say we're looking at a sentence you give a bot. Is it a bad sentence? Does it evoke fear? Does it evoke positive emotions, etc.? Object character recognition, simple, let's say you're scanning a book, a text. How do you recognize all the text in there and store it in a computer readable format? Robotics. There's a ton of AI involved with robotics because it's literally a robot. Think about like how nice that, think about like, I don't know, all the science fiction novels, like, and movies like Space Odyssey, Westworld, if you guys have watched that. Spam detection, this is one of the age-old classic examples of AI, just determining if your email is spam or not spam. Just a comment, I received an email from UCSD that was considered a spam. I opened the spam email and it says it's from Triton, King Triton. I was like, okay. Energy efficiency, I brought this up earlier. Google did a lot of work into this, just improving energy consumption and use and production. Population modeling, your Twitter and YouTube feed, your Netflix movie suggestions, basically a lot. It's a lot. Usually most people are just experts in like one section. Okay, this chat is going mad. What's happening? All right. So wait, is this my slide? No, Edward, it's your turn.
Okay, so what is a neural network? Fundamentally, a neural network is based on like a computational representation of the human brain.
Wait, Edward, are you talking?
Yeah. Wait, am I muted? No, I don't think
I can hear Edward.
Oh, maybe
okay.
my thing's not working.
Okay, so fundamentally, as I was saying, it's basically just a graph of interconnected neurons that like one allow you to send in like an input image, such as housing data, or no, I meant like an input, which is like housing data, or a raw image, and it like goes through all of the neurons, like getting the values processed and stuff like that, and then it retrieves a transformed data value, such as a housing price prediction or an image label. Neural networks are probably the most common tool that's used in AI currently, since a lot of different fields of AI just use neural networks. Like they just talk about, oh, we're using a X model, and that's basically just a giant neural network that they somehow created a new layer or had a really cool configuration for. So that's what the neural network is. Can you go to the next slide, please? So what is a neuron? A neuron is like a neuron or perceptron, as some people call, well, a perceptron is basically just one neuron, but when there's like multiple perceptrons together, it's actually just called like it's called a neural network. So what it is, it's basically just a building block of what a neural network, of like a overall neural network. And as we mentioned in the previous slide, it's modeled after the neurons in our brain. And the neurons in our brain, this is more like cog stuff, but it's like it uses like an electrical threshold to determine whether the neuron fires or not. Like if the input signal to the neuron is, well, yeah, it's just cog stuff. So if it's large enough, then it'll be able to output into the axon terminals into the other neurons that it's connected to. If it's not large enough, then this won't happen. So the key difference between the neurons in our brain and the neurons in a neural network is that the neurons in our brain fire at the same amplitude, but at different frequencies. So like they have the same amount of like power, but how often these firings occur is different. Whereas neurons in the neural network actually fire at different amplitudes, but at the same frequency, because the neurons have to go through the whole neural network each time. They can't just like sometimes decide not to go through one neuron, or sometimes decide to go through it. And there's some current research into spiking neural networks, which is a more biological mirror of our brain, where some of the neural network parts aren't activated. Yeah. Next slide, please. So what is a neuron? On the left, the first image is fundamentally what a neuron is. It's just basically just a gigantic, well, it's like a really simple math equation where first it takes a set of inputs and evaluates the weighted sum of these inputs. And then after that, a bias term is then added to this set of weighted inputs, and the result is fed through a function to determine what's outputted from the neuron. So as you can see, the function just like z equals b plus summation of all of the input neurons times a weight. Yeah, and then this z value is fed through an activation function, which will output the value from the neuron. And a single neuron functions essentially as a binary classifier for data, as you can see in the second image. So let's say you have two groups of values. One is all x's, and one is all circles. So with a single neuron is able to just like make a split line and split the data between the x's and the circles. And also, I think it's important to mention that activation functions can be linear or nonlinear, but in this case, this is actually linear because the line is just linear. But later on, we'll explain why nonlinear activation functions are much better than linear activation functions. Yeah, so fundamentally, a neural network is just a gigantic amount of these neurons all put together into like multiple layers. And it just basically models a giant function. Because the whole concept behind a neural network is that all models or all data sets can be modeled in a really complex, higher dimensional function. So what a neural network does is essentially tries to find this function. And we'll give like some simple examples of functions that neural networks can model, just to like explain this concept further. So next slide, please. So weights and biases. Weights and biases form the parameters of a neural network and are trainable. They're essentially variable and subject to change as the network essentially learns what the optimal values for these parameters are. And also defines the behavior of the neuron relative to the overall network. So the weights are, what weights are, it's basically the inputs are multiplied by a constant weight, which is variable, and this weight essentially multiplies by, basically just says how important this specific input is relative to the other inputs. So let's say a bigger weight wi indicates that a particular input xi is more important than the other ones, as it would influence the weighted input z more. And then bias is kind of like your bias to the neuron. You can think of it like how important this neuron is relative to all of the neurons in that specific layer. Because a bigger bias would basically indicate that the neuron is more important in the overall network, as it will contribute to a larger activation. And given that larger input, it will also equate to a larger activation value. Next slide, please. So activation functions. So we mentioned before, we talked about weights and biases, and after the values from the input neurons are fed through the weights and biases, they're going to go through activation functions. So what an activation function is that it's basically each layer in the neural network has an activation function, which defines what will be outputted in that specific layer. So the three most common ones are ReLU, sigmoid, and tan, which are all nonlinear functions. So what ReLU is essentially, so basically these activation functions are just like really simple functions that are the building blocks of, hyperbolic tan, that are the building blocks of that are the building blocks of all of the mathematical functions that it will represent. And these are like the graphs for these activation functions. And we can see that like the most important change usually happens between -1 and 1. So generally, the data is normalized to be between -1 and 1. Yeah, hyperbolic tan. I'm pretty sure it's called hyperbolic tan. Yeah. And linear versus nonlinear. So you can just expect, or you may be thinking why we can't just plug in everything into y equals mx, because we can technically model everything with just an infinite set of lines. Well, I mean, this is technically possible, but it's like really annoying to do. Like it'll take an insane amount of neurons to model something like a circle or just like a little simple sine curve. However, if we use a more nonlinear activation, like if we use hyperbolic tan or sigmoid, we can more easily model such a curve. And yeah, so that's why we kind of want to introduce nonlinearity into the neural network. And with only linear activation, we only get like a limited prediction set, as it'll just simply be linear regression. Like it'll just imagine like a lot of lines just like crossing over the data, and that's basically what's going to be going on. And yeah, so I guess the main takeaway is that, yeah, you can use linear activations for your whole neural network, but it's going to be not as good as if you just use nonlinears. Because I feel like with linears, it'll take like a much more to model a simple curve compared to the other ones. So next slide, please. And so this is just like a simple comparison between linear and nonlinear activations. And these are kind of like the problems with linear and why we should be using nonlinear functions. So the first problem with linear is that it has quote unquote constant learning, because how neural networks train is they use backpropagation of a linear function, which is essentially taking the derivative of a linear equation or whatever activation function that is being fed through. And the derivative of a linear function is just a constant. So there won't be a relation between the input and the derivative output. So essentially the neural network isn't necessarily learning anything new about whatever data was inputted. And also you can't have multiple layers, because linear combinations of linear functions is just still linear, because the model is essentially just one giant linear. I think the function is because it's like matrix multiplication, yeah. It's like just a lot of matrix multiplication. So in the end, even if you have multiple layers, it's just going to be one giant layer. And then it's kind of useless. You won't be able to have hidden layers. And so this is why we should use nonlinear, because it allows for backpropagation, because the derivatives of those curvy equations is not a constant. And we can also have multiple layers, because they don't just essentially turn into the same one. It's not linear stuff. Yeah. And Stone will just start going, and we'll start going over some simple examples of what we can do with a neural network, and just like kind of ramp up the complexity throughout.
Oops. Hi, y'all. Oops, wrong slide. So just a simple example. Ever has provided us some amazing graphics here. 2 giant ellipses represent our 2 neurons. So here's a simple example. 1 input, 1 output. Just a single neuron. Since neural networks are just representations of complex math equations, we can really just use and to model any math equations. So let's take the equation y equals 3x plus 5. For example, if you plug in a value 1, right, we should get 3, and then the next step we to update it plus 5 and get 8. You notice that this function is really mx plus b, but in machine learning, we change that to wx plus b, where w is our weights. So in this case, our weight here would be 3, and our bias would be 5. I don't know if we need code for this. I think this should be pretty straightforward, but if you guys want to see code, this is how it works. You do a weight equals 3, bias equals 5. You just do W times A plus B, and that's your prediction. Very simple, and this is Python. It's a very simple implementation, but let's ignore that for now. Anyone has any questions? So what's bias again? Just an attic. Okay, maybe I can explain bias a little bit more. So bias is just a constant offset. I'm gonna go back to the slide we talked about that because we might have gone through a little fast. So this is our effective update equation. So for each input neuron, we have this each inputs, right? X1, X2, Xn. Each of them are associated with one weight. And what we do is we do a dot product, or we just multiply pairwise the weight with the input. After that, we add them all together to get ourselves what's called a weighted input, and we add the bias. Z forms our effective input that we then pass to the activation function F. Does anyone else have any questions? Because I know this part of the math, this is where math starts, and math is always a hard thing to do. What's the most complicated math you need to know for, we'll probably talk about that at the end of the workshop. We'll have a quick Q&A session at the end. But is everyone cool with the sigma notation? Okay. So this is a simple example. Sorry? Hello? Okay. So in this case, our W1, our first weight is 3. Our X1 is just X here. And our bias is 5. Next up. Here's a more complicated example. So if you guys have learned anything about computer science, you might have heard something called an OR gate. If you guys know what truth tables are, let me quickly explain them. We have a truth table at the top right. Can you guys see my mouse by any chance?
Yes.
All right. So at the top right here of our truth table, which is saying for whatever value A and B, what is our output value? So this is the OR gate. When we have two zeros, when A and B are both false or 0, our output should be 0. If A and B are different, our output should be 1. And if A and B are the same and they're 1, the output is 1. This is what's called OR gate. You might also recognize this simply as an OR statement in Python or computer science, where you do like true or false, true or true, false or false, etc. So in an example of our OR gate, our perceptron rule here is going to be if y is greater than 0, we return true. If y is less than or equal to 0, the output here, output neuron, we return false. As an example, if we plug in A equals 1, B equals 0, our expectation is the output is 1. And let's look at this neural network model we have here, for example. The reason why if we set the weight 1 equal to 2, we set weight 2 equal to 2. Remember, we first do our weighted input. We multiply all the weights by the inputs. So x1 times w1, 2 times 1 is equal to 2. And then we do x2 times w2. x2 in our case is b now, which is 0, and times 2 is 0. This forms the value of 2, and then now we add our bias. So after doing wx, which gave us 2, we now need to add b, which is -1, which equals 1. And now since our output y is 1 is greater than 0, we return true. So in this example, our OR gate works. Any other questions about this example? After this slide, I'm going to hide some of the neural networks and see if you guys can come up with yourself. All right? I see unhappy faces. Okay. Yeah, next slide. This one is going to be an extension, but let's see if you can try to do this. So our first one, you can try to make yourself, take a piece of paper, draw the weights, draw the biases. What I want you to do is make a neural network with 3 input neurons connected to 1 output neuron, and the output value is the average of the 3 inputs. So for example, let's say our input vector is A equals 1, B equals 0, C equals 3. Obviously, the average here is 1 plus 0 plus 3 divided by 3, which gives us 1.333. I'll give you guys a quick moment. If you guys have questions, we can talk about them. Also, I'm just saying, I think there's definitely more than one way to do average of 3 numbers. You can make something super complex to just do an average. Like you can have, yes, these are all linear activation, remember. Just remember, like sometimes you can do like, I think a 20 layer network just to do a simple task. It also does the same thing. But yeah, I'll give you guys another minute and a half. Then I'll go and show the solution. You're trying to make an average function that takes 3 inputs and returns the average of the 3 inputs. Wait, Edward, did you make code for this? I don't remember. Oh, I made code for this. Okay, never mind. I'll show this later. Okay, I'll go write the code actually. Give me a second. Let's define an average. Okay, I'm not gonna write the answers yet, but I'll give you guys a hint. In our neural network, we're gonna have 3 weights because we have 3 input neurons and 1 output neuron. I'm not gonna write the weights yet. You guys can go figure that out. And of course, we have a bias. And remember the update step, we do our pairwise multiplication, a dot product of our inputs and our weights. And then we add our bias. This forms our Z, perform our linear activation on Z, and that returns our value. Okay, all right, I'm gonna show the answer. 3, 2, 1, go. So this is an answer, very easy. You literally make a weight of 0.33 or 1/3 on each of the weights, and you set a bias term of 0. And this is pretty obvious. We know that in our average function, every input influences the final result by a factor of 1/3. So we're saying each of our inputs has a importance level of 1/3 out of 1. If you want to see this in action, we'll show it right here. So let's say this. These are our 3 weights, so all the same, and our bias term is 0. Why is the weight 0.33? Because we're taking the average of 3 numbers. So if you recall, the formula for taking the average of n numbers, or 3 numbers in our case, is numbers a plus b plus c, parentheses, divided by 3. Yeah, so each input will get 1/3 weighting. Thank you, Ishan. And let's just quickly look at this. Let's just call Python n.py. There we go. We see that the average of 103 gives us 1.33. You can try another example. Let's print the average of 100, 200, and 300. Nice, 200. If you do some quick maths, 100 plus 200 plus 300 is 600. Divided by 3 gives you 200. All right, I'm gonna leave this code in here and I'll commit it later. All right, next one. Oh, wait. This has an answer first, wait. Wait. Wait a second. Okay, you know what? Whatever. You guys have seen it. I'm gonna, oh wait, you know what I can do? Easy. Wait. Give you a random picture. I'm gonna cover this. All right. This works. Simple, this is the next example. So let's try to see if you can do an advanced absolute difference neural network. I already took a screenshot. Okay. Oh, this tells you an answer here. Never mind. I shouldn't show that either. Is the next slide also? Oh, wait, the next slide's still hard though. Okay, but I'll cover the next slide as well. I'll give you guys a few minutes. Wait, did you write a function for this as well? Oh, we don't have it. But, nope. Let me cover this. Okay, I messed up. give you guys another minute or two. Oh, also, this is a good book. You should read it. By Don Norman. He's our design director at UCSD. Oh, someone gave me a good suggestion. I should just pause screen share or frozen and then make changes to the slide. I'll do that next time. This is a slight mess up. Wait, who's this sponsored? What happened? Sell out. Gotta get those funds. Okay. Anyway, I'm gonna reveal the answer in 3, 2, 1, go. All right. So this is a little different. We kind of, well, we use something called parametric ReLU, but it's actually really just, yeah, it's called parametric ReLU, but it's basically an absolute value function. So if you look at what this parametric ReLU activation function, it resembles a ReLU function in the fact that we return x if x is greater than 0, but in the other case, instead of returning 0, we return ax. And what we do is we set the value, to make it an absolute value function, we set a equal to -1. So we return the negative of x if x is less than 0 and just x if x is greater than 0. And if you graph that out, you'll see that it's a simple absolute function. This makes our absolute difference neural network pretty easy. All we have to do is just figure out the weights. We just put W1, W2, W1 equals 1, W2 equals -1, and we get our absolute difference, which is, as you all know, x1 minus x2 absolute value. We're done. We can just put a bias term of 0 because this works fine. Okay. Any questions or anything? All right, we're gonna move to the next one. I'm gonna cover the slide. Okay, wait. No, wait, no. What? There we go, covered. Okay, this one's a lot harder. Yeah, Edward, explain it.
Okay, so for this one, all we want to do is we just want to, for this one, we actually have to use multiple layers since we aren't able to use like a simple, we aren't able to use like a simple function just to model this equation. We would have to use at least one additional layer. So for this one, we're basically building on what we did in the previous one using this parametric ReLU. And we can see that we also have this absolute difference inside this equation. And all we have to do is just make like 1 or 2 more layers, and then we can make this into an equation that outputs if the absolute difference is between 1 and 3, outputs true, and or also output 0 or negative values if it's not between 1 and 3. Yeah, so you can like try that out.
You're muted.
Okay. Someone just asked about absolute value, y is bias equals 0. If you think about it, we're effectively just doing this. We want to calculate x1 minus x2, right? But what we're given is, if you look at the coefficients, right? Weights are like the coefficients. We're effectively putting W2 here and W1 here. And we see that W2 here really is just -1, right? So we can stuff in -1. And we see W1 here is just 1. But you see there's no room for a bias term. Where we wouldn't have a bias at 0. Yeah, so if we think about mx plus b, that really common linear graph question, I don't know what it's called. Let me go back to that slide. Here is an example where bias is 5, and also OR gate. But here's a really simple example. if this doesn't make sense, I can also explain the OR gate one. Sometimes the bias helps us. If you remember conceptually, biases influence the overall network, not just the weighted inputs. So we see that we need this bias of -1 in order for this OR gate to function properly. If you try fitting in other inputs of A and B, you'll see that the bias of -1 ensures that we get the correct output. Okay, back to the slide. Yeah, if you look at our code, our OR gate actually has this. So we have our weighted input equals to 2, our first weight, times input 1, 2 times our input 2, and plus our bias of -1. And we perform our linear activation, and we return a result. Yeah. Okay, Edward, how much more time do you want to give people?
I think this is enough time.
All right, we're gonna show the answer in 3. I mean, you guys can already see the answer, but like I'm gonna show it in 3, 2, 1. Ta-ta! This looks very complicated. Explain it, please.
Okay, so we're basically just using the first layer to just get the absolute difference. Doing weight 1 for the first one and weight -1 for the second one, we'll find the sum or the difference between the first one and the second one. And if we use the parametric ReLU activation with a equals -1, it'll just find the absolute value of the difference between the two. And then we have weight equals 0 because we don't want to add anything necessarily. Wait. No, this is weight equals 1. Saved it. Okay, yeah, weight equals 1. And then we want the weight equal to 1 because we want to just pass this direct value into the next layer. And in the second layer of parametric ReLU, the objective is just to essentially move this equation from being between 1 and 3 to being between -1 and 1. And since we know that our parametric ReLU works specifically at between -1 and 1, or that's where like the changes between those two, then moving this absolute sum between those two values will result in any values between any sum differences between 1 and 3 becoming a value greater than 1, whereas any value that is greater than that will just become like a really large value. So yeah, that's the whole purpose of the second node, is just to normalize the data and move it between -1 and 1. And then the last layer has the trick for the last layer is that we use the weight of -1. By using a weight of -1, we essentially flip over the input into the tan function. So we know that the input to the tan function has activation such that when it's greater than what's it called? When it's greater than, yeah, okay. So when it's greater than any value that's greater than 1, or no, when it's -10, any value that's greater than 1 will become a negative value, and anything less than -1 will become a positive value. So after applying tan into this, we can get a positive value out. So yeah, that's the whole objective of that. And then bias equals 1 just moves all the biases up 1. So then all the positive values are just values where the absolute difference between 1 and 3 are positive. Yeah, I think that's how you do it. Yeah. Wait, Stone, can you show the code?
Do you have code for this one?
Yeah,
I couldn't find it.
It's in vectorized.py.
Oh, you put it in here with mine. Oh,
Yeah.
Okay. This looks very complicated, but yeah, this is the code. Let me hide this one and hide this. All right. So this is a code. This starts using some vectors, which I'll explain later. But effectively, what we're doing is we're taking our weight one, right? We're taking our weights, map moling it. This map mol function. So we're gonna give you guys a quick intro to like NumPy, but the only functions you really need to know is np.array and np.mapmol. np.array initializes a matrix for you. That's a NumPy array, which has a lot more features than just standard Python lists. memp.matmul does a matrix multiplication, which I'll go to in the next slides. So here we take our weighted input, matmul, w1 x plus b1 standard function, and that's this part here. And we feed it into this activation function parametric ReLU, which we put here. We feed in a equals to -1, feed it in weighted input, and we get our output 1, which goes to our next parametric ReLU neuron, activation neuron. So we get our weights again. Recall that our weight here is just 0, which we do here, add the bias -2, get our weighted input, continue on, so forth, so forth. So just make sure to follow this code. This looks a little complicated because we're doing matrix multiplications, but I'll show an example of matrix multiplications using the average example. So if we run this real quick, you'll see that this gives us a nice value. All right, where is the next thing? Okay, this is the hard part. This is the hardest part of the workshop that you need to understand. Why is this math 18 lecture 90 minutes long? What? This is computer science. What are you talking about? So the last thing is we need to talk about the vectors because it's very important. We can't hard code everything. Yeah, so in program, we'll talk about this later in the next workshop about learning. But effectively in any program, we have this network. It's your model, it's your computational model with parameters that you want to fit, change, and adjust such that it predicts more correctly. The reason why we want to use vectorized inputs is, for example, if you look at our code, you'll see that I hard code a bunch of things. For example, this average function, I hard coded the weights like this, W1, W2, W3, and the bias, and each layer. But the issue is, what if you have more layers? What if you have n weights? We're not gonna want to type out every single weight. So this is what we do. What we do is we generalize it. We store weights in a giant matrix. Just an explanation of how this matrix works. First, let's understand our input. Our input, let's say, has n dimensions, which means that it's basically n, has n rows. So you'll see here, our vector x is composed of values x1, x2, all the way to xn. And you'll see what we're going to find here is n is our input dimension. M as in mom is our output dimension. So here's a quick primer on just matrices. Let me see, where do I write this? If you have a matrix W and X, you can multiply matrices of the form m times n. So W is m times n. And you can multiply with another matrix of the form n times k. So here you'll see that Wx is a valid operation where we do a m times n array matrix, which means m rows, n columns, multiplied by a n by 1 column vector. If you don't remember how matrix multiplication works, don't worry. I always forget too. But feel free to search online real quick. It's really simple math. But a really nice way of looking when you're multiplying a matrix like this, as a block matrix with a column vector, is you take the first row, multiply it by this column, store it here. Take the second row, multiply the entire thing. Take the next row, multiply by the entire thing, and so forth, so forth. And then for bias term, we do the same thing. We vectorize it by just adding the bias vector. And then just produce our result vector. So you recall that before we've been dealing with simple one output neural networks. But by using vectors, it makes it easier for us to do multi-output vectors. So now let's take an example of average of 3 numbers. Right? Remember, this is our neural network. We have weights of 0.33, 0.33, 0.33. Now let's first think about the matrices. Our input layer, right, has 3 neurons. Our output layer has 1 neuron. So now what we know, our weight matrix is going to be composed of 3 weights, W1, W2, W3, and this is going to be a 1x3 matrix. The reason why is 1x3, and this is a little bit backwards, but you'll get used to the notation. The way we figure out the dimension of a matrix in a neural network is taking the number of neurons in the next layer times number of neurons in the previous layer. So you see that the number of neurons in the next layer is 1. Number of neurons in the previous layer is 3. Therefore, our weight matrix is 1x3. And in code, this is how I code it up. Here we go. So I store weights here. Weights equals np.array, and I put the 3 values. This is a 1x3 matrix. Next, we have the input column vector. So our input column vector is x. I initialize it as a simple 3x1 column vector. Now, our input column vector x is composed of x1, x2, x3, and the way we figure out the dimensions is simple. You do the same order. The layers on is that number of neurons times x, right? Number of neurons in the next layer. So it's 3x1 matrix. And remember matrix multiplication rules, we can multiply a 1x3 matrix with a 3x1 matrix because they both share the same 3 in the middle. So once we do that, we see that the weight matrix multiplied by the input matrix gives a 1x1 result matrix, which makes sense because y is a single output value. So let's see this in action. Let's print this. Let's not print that, let's not print that. Nice, so 2 plus 3 plus 4 gives us 9. Average is in 3. Any questions about the matrix multiplication? And yeah, we use matmul here. So this function here is equivalent to this equation here. Wx plus bl, multiply weights and x, and then plus bias. Someone just asked something about one-hot coding. That's outside the scope of this workshop. We might be bringing it up in the next workshop, but someone can explain it. Yeah, neurons in the next layer is a number of rows for the weight matrix. Correct. Any other questions about this? Any confusion or anything? Yeah, I'll show you guys a difference. So here's our weight. Here's our one using matrix. Here's the one that doesn't use a matrix. Let me delete this. So here we hard code the 3 weights like this. Oh wait, let me see if I can put into 2 screens. Oh, let's go. All right, here's a difference. So this looks really similar actually. The main difference is that one of them we put them to array, the other one we hard code them to 3 separate values. Same for here, we're doing a matrix multiplication here, whereas here we're doing the matrix multiplication by hand effectively. Any other questions about matrices and vectorization? And don't worry if you don't get this too much. We're gonna make sure by next workshop, you guys have a better understanding of NumPy. Yeah, makes calculating outputs a little bit easier and also faster. But we're gonna have a better understanding of NumPy by next workshop and also introduce you guys to more vector notation because that's really important for learning in neural network. So far, this entire workshop, we've been doing what's called feed forward. We take an input, we pass it through the neural network, and we get the results. The second part of neural networks that's really important is learning, where we pass it backwards and we adjust the weights. Right now, we're just kind of like deciding the weights ourselves, but in true machine learning, you got to make the machine decide the weights. Anyway, any other comments? Backprop, yeah, we're going to talk about that next workshop. It's a little more complicated. It's a bit of math, but we're going to try to make it as simple as for everyone to understand and also include code. Okay, I'm going to show you guys something cool. Oops. So this is called the Playground by Google using TensorFlow. This is also where I got the picture from. So you'll see, this is much more complicated. Let me first train this. So what you're seeing right now is the neural network training, which we'll bring up next workshop. The neural network in training mode effectively is adjusting a weight so that it produces this little boundary here. This is what's known as the decision boundary, which decides whether this data point, this little circle, is blue or it should be recognized as orange. Now let's just stop this. So the way we decide, so let's say we have a new data point, right? And we feed it through the network here. This is our network, which appears to be a 2-4-2 network. 3 layers with 2 neurons in the first one, 4 neurons in the second one, 2 neurons in the output layer. We see that the output that is being returned by these 2 neurons at the output is actually the XY coordinates. And we see that the 2 neurons fed into here is also XY coordinates. Oh, actually, I'm not sure what these two neurons are for. I think these are combined together to create the distributed boundary, sorry. And you see that these 4 neurons in the middle, interestingly, are kind of like in the midway. You see, like if you combine all these 4 images together, you kind of just sort of just get this image. Oh yeah, if you haven't heard, we have a reading group tomorrow. It's open to everyone. If you don't know that much AI, this workshop probably primes you well enough to understand what we're going to do tomorrow. Yeah, I highly encourage you guys to check out this website and just play around the neurons, add more layers, make more hidden layers, see what happens. Train it. So you press the play button to train it and see how well it learns. You can also get rid of layers and see how badly it learns. But let's say you have a really simple network. It probably won't learn very well. And this is why also we want to have many neurons and many layers. Because if you don't have many, you're just going to give yourself a linear classifier, which doesn't work for all data types. Any confusions, any questions or anything? What's the purpose of a layer? Yeah, so the purpose of a layer is it's a computational model of prediction, effectively. Each layer builds upon a previous layer to predict more accurately, or sorry, change the input to match some output or predict and make some output. I really don't have a good definition of what the purpose of a layer is, but it's basically serves as a prediction layer. You feed it input and it gives you output. Someone just asked, can you go over activation again? Yeah, I can quickly touch on activation. Wait, Edward, do you want to say anything else? I know you have to leave soon.
No, I think you're doing a good job.
Okay, thank you, Edward. Let's go back to activation. So activation function, let's go back to neurons. Think about biology and a neuron. A neuron is actually a computer, effectively. It takes an input and produces an output. So the way we produce an output is first we take our input, we apply a function on it, and then we get our output. That function is known as the activation function. So this function here, f, we take our input by taking what's called a weighted input of the weights times the inputs plus the bias. We apply our activation function, and it gives us a result. Yeah, so layers allow you to utilize more activation functions since each layer has one type of activation. And another important thing about activation functions is that it introduces something called as nonlinearity if you use the right activation functions. So I'll show you back to this neural network playground. Can we change the, here we go. I'll show you an example. This should not work. Here we go. So you see in this data set, we have like a really weird circle thing. If we use our eyes, we can gauge that the right decision boundary should be a circle, not a line. Yes, you have to provide activation functions typically. You'll see that we got a line, but what's the issue here? We have a complicated looking model of many neurons, but it doesn't seem to be learning properly. It doesn't seem to know how to decide, right? So how do we fix this? We use a nonlinear training activation. So right now, all of these layers are using linear activations, but if you just stack linear functions upon linear functions upon linear functions, your overall neural network is only capable of modeling linear functions. So for example, let's look at this data set. Clearly in this data set, we just need a simple line to divide these two lines. If you look at this, trains perfectly, very perfect. Has a training loss of 0, which means it got all of the answers correct. But now if we go to something more complicated like this, it can't seem to train anymore. So what we do, we introduce nonlinearity using, let's say, the sigmoid function. The sigmoid activation function, which to remind you guys, is this one right here. You see how this is nonlinear because it curves up and down. More mathematically speaking, the reason why this helps the neural network produce more complicated things is 1, it's not linear. 2, the derivative is not constant. So changes are more better. So if we train again, okay, let me make the neural network smaller. I made it too big. Oh, I need to reset, sorry. Wait, what is happening here? I need to do 10H. Okay, not all of the activation functions work properly. And you'll notice there's a bunch of parameters here, like regularization, learning rate. Depending on the activation function you use, different learning rates, different regulation rates will affect what's going to happen. Yes, so most of all the example NNs we showed today were using linear, except for the one using parametric ReLU. So when we're doing absolute difference, if you recall, the absolute difference function is a V shape, right? That's not linear. So we have to use a special function, which is nonlinear, to model that. Any other questions? So what do you, wait, so do you choose one function for the whole network? You can, but you can also do different functions per network. Yes, in theory, you can do any random function. As long as the function is differentiable, you can learn. And we'll talk about why we need differentiability and why you're capable of learning in the next workshop. Okay, any other questions? Here's the resources. These are 2 main links you guys should know about. Someone just asked me a question. How do we know which function to use? That's a very not exact science. I think Edward probably could have a better answer.
Wait, what was the question?
Which function do you use? Like, how do you know which one's better, or which one do you want to use?
Well, it generally depends on the type of data that you're presented and what's the objective of specific layers. Because I'm not particularly sure of why you would probably choose sigmoid over hyperbolic tan, but there's another one called, I think it's called sigmoid? No, so it's basically, those are just like the curvy ones, which are like that, like hyperbolic tan. For those, the whole objective of those is just like to model like some like kind of like circle kind of thing, because you want to try to imagine like someone's plotting out all your data and how you would try to draw like lines that like surround the data and separate it into specific groups of data. For linear ones, you want to use it when the data can be easily split apart using just like a couple lines or something like that. And for stuff like sigmoid and tan, it's more like nonlinear data. It's probably like a really bad representation, but like sometimes you also have to like think of how fast the thing goes to 1. Generally, like functions that go to 1 faster mean that the values are going to be really quickly converging to 1 or -1, and those are better used for more binary operations, such as determining whether something is a certain thing or not. Whereas stuff like sigmoid are used more commonly just to represent like curved things. There's one, I think it's called sigmoid. There is, for one specific type of neuron, it's used a lot in classification just because the whole intent of this type of neuron was for classification. It's called softmax, yeah. So what softmax does, it takes like the sum of all the different outputs and then outputs essentially just a value between 0 and 1, which essentially is like the prediction probability that said output is a specific class. So generally you would want to use softmaxes in the last layer of a classification model, since that will represent what type of object it is. So let's say so for something with like 10 different, so it's like especially useful for something with like multiple classes, because then you can just it'll just output the probability that it's each of the classes. And then for a classification model, you just probably use the top 1 or 2 classes or the values that are outputted the highest from the softmax function.
Here's softmax. Let me go find it. That's not softmax. Wait.
It's better to represent softmax as the equation itself, because the curve doesn't actually say that much about it. Like, yeah, the middle picture, yeah.
This is very complicated looking, but there you go, guys.
It's just like a sum.
Yeah. Softmax basically condenses your outputs into something that makes sense. So if you guys know, like sometimes like, I don't know, like those image recognition tools, they'll give you a percentage probability of how confident they are. It's basically the result of a softmax activation layer. Yeah, some of you guys are asking if you can use this knowledge for our AI competition. Not gonna lie, you're gonna need a lot more experience with neural networks or using neural networks in a competition like that. But Edward came up with an ingenious idea the other day. We're gonna have a neural networks competition after our workshops. We might do one even earlier, I don't know, but effectively wait, Edward, do you want to explain your competition idea for neural networks?
Okay, so for this competition, it's gonna essentially use the knowledge that we have gained from these workshops to create a neural network. So we're going to give you like a specific function. We won't tell you what this function is. We're just going to provide you with the inputs and the outputs for this function. And the whole purpose of this competition is that you want to model this function as closely as possible. So, and we're going to try to make it so then it's more, what's the word, generalizable. So let's say we're only going to give you values from the domain -1 and 1, but we would want you to predict outputs up to -1.5 to 1.5. Yeah, so whoever has like the highest training accuracy for this will be the winner, I guess. And you can like plot out the input data or whatever you want.
Yeah. I don't know what Edward's gonna do. He's probably gonna combine like a random, I don't know what you can do. Yeah. But we'll probably release a competition definitely after the second workshop because you probably can't do it if you don't know how to learn in a neural network. So that's when it's going to be released. I don't know how many of these we're going to do because they're pretty easy to make. All we have to do is put a leaderboard online and let you submit files. But yeah, it's going to be fun. When's second workshop? Next week, same time. Make sure just to listen out for the announcements page on Discord. You can also check our website, ai.acmu60.com, for details of what are our upcoming workshops. Okay, there's still 63 of you guys here. That's amazing. Do you guys have homework? No. I encourage you guys to practice using NumPy. Definitely, yes, homework is to join in Discord, yeah. The other homework is to compete in all our competitions. We have one next week, next Wednesday. And then we have Everest competition, which is your modeling competition coming up soon. But if you want some more realistic things, some things I suggest you guys to look in is refresh yourself on how to multiply matrices. If you know that, you're gonna be pretty set for all the math. And then also refresh yourself on how to do derivatives. Because backpropagation will involve some derivative work. Is this session recorded? Yes, it's still being recorded as far as I know. We will post it, it'll be uploaded to YouTube and then we'll post a link once it's done. What else? Why are we not using ACM Live? I think ACM Live has some issues or something. It's meant to auto upload to YouTube, but they're not doing that right now. And I'm actually not sure how do we get the recordings from ACM Live. So we're using Zoom for now. Yeah, next workshop, Edward, Jason, Vega, and Catherine Lee are gonna be running it, I think. Bye, Bryce. Does anyone have any questions? I know a lot of people are still confused about the really complicated multilayer network. Someone just asked, I'm a first year CSE 11 in Math 20C. Is this going to be too challenging for me? Well, okay. Since you're doing Math 20C, you're gonna have enough kind of math knowledge to at least understand derivatives, which would be good for our next workshop. The kind of derivatives you need to know for multivariate calculus is basically the same thing as single variable. You just do a couple of extra things. Trust me, you'll learn about it. For CSC11, does not hold, unfortunately, CSC11 is not in Python. I highly encourage you to learn Python because all of our codes can be in Python. We do not have workshops in Python. That's mostly because ACM Hack, one of the other subworks of ACM, does all the workshops on like programming languages and frameworks. So I highly suggest checking them out to learn about Python, or you can just go online and find a tutorial. Who just called himself Stone Tao? All right. Is it William? No, William's William Dwan. What else is there? Yo, who's playing the video? Oh, he played the video of ACM. No, Alvin Wong's in here. He's not. Okay, whatever. Does anyone want us to go through the code again, like how the multi-layer neural network works? Yep, I'll explain it one more time. Or Ever, do you want to explain it, or? Oh wait, I have to code though. Okay, I just shouldn't be too hard to explain. Okay. First thing to remember, what is the weighted input, right? The weighted input is what goes into each neuron. So the weighted input for the second layer here is the sum of x1 times w1 plus x2 times w2. Good? All right. And then after that, we add the bias. So let's look in our code. We do this here. We store in our array, our matrix, the two weights, 1 and -1, w1 and w2. Good. Okay. Bias is 0. So our weighted input is now the matrix multiplication of w1 input. If you don't know what this looks like, it's basically the code here. x1 times w1 plus x2 times w2 is the same thing. And then we add the bias term. All right. If you have any questions, just ping me immediately or speak up. So now we store our output, which we apply our parametric activation function here. And recall that we set the a value of parametric ReLU to a equals -1. So we put -1, we give it the weighted input, and we get our output. So at line 70, here, let me label this as layer. So this is layer 2. Wait, this is called output 1. This is confusing. Wait, Edward, do you mind me if I change the name real quick? Can you sort biases and matrix and do matrix addition? Yes. In fact, actually what NumPy does is if we add a constant scalar term like b1, it auto expands it into a column vector, or auto expands it into the same size and shape of this matrix here. Does that make sense, Kunal? So let's say np.map_mul here returned a 3x3 matrix. B1 will be added to every term. Let me quickly label this. This is output layer 2. This is output layer 3. You see how all this actually nicely like kind of ties together, layer by layer. So this is output layer 2, and now we begin layer 3. So remember, the layer 3 here takes the weights from layer 2, right, and creates a weighted input from layer 2. So weighted input 2 produces output of layer 3, right, which is here. And you recall this is the correct weighted input. Simply we take our weight of 1, add the bias -2, right, and matrix multiply. Why the bias is -2? This is just to shift this into the range, if I recall correctly. You see that how's a equals -1 chosen? Okay, you know what? I'm gonna go Desmos. This would make the most sense. I'll show you guys what ReLU looks like. So here's ReLU. ReLU looks like, is this how you do the Desmos thing? Wait. Does anyone know how to do the parametric graphs, or like, what's it called? The bounded ones. Okay, wait. Nope. That's not the right thing. Range restrictions. Oh, okay. So let's do x for x greater than 0. So ReLU looks like this. This is the ReLU function. Let me change the color. Bro, how do you change color? Does anyone know how to change color? Nope.
Wait, Stone, you could change the color if you click on the wavy line.
No?
Just kidding.
Okay, I'm just gonna spam until I get red. There we go. So this is called ReLU, but you recall that the function we want to get is this, right? This is our absolute value function, right? So the way we get this is we get ReLU and then we do it backwards. So this is parametric ReLU. Let's just do less than or equal to. Okay, let me just spam this until I get purple, green. Green, there we go. So you see here, the function we want is this blue line, but it's not right. So if we set a equal to -1, we get the same function. Oh, that's how you change color. Okay. I'm being stupid. But does this make sense now? The a equals -1 with the parametric ReLU. So changing this changes our parametric ReLU function. If you set it to 0, it's normal ReLU. If you set it to -1, it's the absolute function. Someone earlier asked a question about the bias being -2. You notice it's -2 because you want to shift this into the range 1 less than this, less than 3. After that, we do a tan-H thing because you want to return output true of this greater than 0 and output less than or equal to 0. And then we see this in code here, tan-H activation of the weighted input. Do you ever change a in activation function, or do you usually use parametric ReLU of a equals -1? I think you never use a equals -1. That's pretty rare. Typically with ReLU, you just have a equals 0 or like a equals, I don't know, just 0. It's not common to do this. This is just an example. Yeah, we just use a equals -1, but that's for example for absolute value function, which is a very particular example. Anyone else? There's still like 30 of you guys here, damn. Does anyone want more understanding of the biological side, or I don't know, cool things you can do in AI? Oh, okay. Go, Edward, go. Okay, I'm gonna, thank you. Yeah, no problem. Just be here for next workshop. That's all we ask. And our competitions. I'm gonna stop the recording now because I think this is going really long. So I'm gonna stop this. Stop recording.